Okay, let's get started. Let me share my screen. And so we okay. Last time we left off to kind of motivate why we need uh, uh weight initialization. So basically, if you look at let me just copy this again. Or maybe I just move here like for the moment. So if we consider like randomly initialized weight, like if it's too small, then like basically the output at each level, say, or like especially in the deeper level, it just goes to zero. So when it goes to zero, definitely like yeah, it's not going to work. Basically, all the outputs will be zero. And on the other hand, if the weights are too big, then like you actually basically like you saturate it somehow. And of course, like if you here like we're showing like using, I think it's using 10x here. So then like in that case, like whenever you saturate it, like it's like as you mentioned, like, if you think of like for example this layer, the activation function is like that, right? If you saturate it, you're either here and here. Either way, like the gradient, the local gradient here is zero. So there's no, then whenever you back pop, you go back to the train rule here, right? So you have the, let's say I have y here, I have x here, and I want to compute the partial derivative of like the final loss with respect to x. So that will be a partial loss with respect to y and then y with x, right? So the local gradient for this activation function is zero. So then like nothing can pass back. So when you are saturated. So even if you are not using like 10H or like sigmoid as activation function that will eventually level off, even if you use value, say, but then like because you have so many precision, right? I mean, for to represent numbers, um, if you if your weight is too big, eventually it will just blows up, and then like you will have like probably NAN somehow like, and if you're under four also like either over or under four, like you will have like just end up like numerical issues as well. So either way, we want to make sure that like your weight are kind of like um, appropriately initialized so that it's not too big or too small. So here I will just give a uh, kind of a uh, high level. It's not exactly high level, actually sufficient detail, but I'm not going to talk about all kind of initialization, but I just kind of give a idea like how the people could do like initialization really. So consider like the case when I have let's say a multiple layer here. I have W1, let's say as the weight, W2 and so on, W3 here. So for the moment, I assume the activation function is just dummy, maybe just an identity function. So that you can think of like the activation function is not there. So then like what we want is like we want to have, let's see, I want to use the same notation as in my slides there. Um, I don't have like particular notation honestly, so it's okay. So I have let's say just x and y here, just x and y. So what I want is like, let's say if I have the, if I have many layers as I continue to go I mean go deeper and deeper, um maybe I can use a notation here. Say x1 is first layer, then output like y1, and then y1 is plug it back like this is the same thing as like this x2 is equal to y1 here. If I have like the activation function is just identity, I have y2 and so on and so forth. Now I want to make sure this output is not too big and too small. So then the thing is, okay, first thing like let's make things simple. So let's assume the inputs is like zero mean already. Again, like this is often like what people do is I assume this is zero mean. So if not, I can subtract the mean, right? If this is zero mean, then the variance of x will be just equal to the expectation square. So I have like, let's say, uh, I want to look at like essentially I want to make sure that like up to several layers, maybe like up to many layers here, I have like, let's say, the xn here. I want to have this like xn here. Uh, this is like basically you can think of the energy of this signal here, right? The xn here, uh, it still has the approximately the same energy as like at the beginning. So does it make sense? Like this is the main idea here. So or to make sure that like to guarantee that like what we're supposed to do is simply like for each of the level, I want to make sure that like the energy after the ith layer is just the same as like the energy of the input. Like basically output of the ith layer is just the same as the input of the ith layer here. Actually, just to make sure I have like good rotation, I probably supposed to use cap. Yeah. So, and as I said, like we already assume that like things are still mean, and then like so therefore like this variant, oh sorry, this um expectation y square is actually essentially the same as the variance as that as well, right? Um, and this is like the variance of also. So it's like essentially we are just what we want is really we want the variance is not going to change uh after we're going through this layer here. So then like okay, so that okay. What was y though? Well, y is essentially just like wx, right? So let me remove the index here because let's just consider any arbitrary layer. I want to make sure that again like the variance of y is approximate variance of x, and then y is just equal to wx, right? Assuming I absorb the bias into x somehow. Um, then I have this therefore like variance of y uh, is a variance of like I can write it as a summation. I guess like does it help or not? Yeah, okay. Let me write it as a summation. So summation of like wi xi. So and some of the index I here. Let's say I is like equal to maybe 1 to n. So that is basically what's going on here is I have uh, this is uh, this is sum here, right? I have like several of these W1, W2. This is weighted sum of this up to Wn. And I have X1, or actually Xn here, right? I got the Y here. So now if I assume this X are independent, like if I can assume this X are actually not even independent, if I can make it a weaker condition, it's just uncorrelated. By the way, like this is a little bit I don't know, like actually maybe I want to see like how much background you guys have like this kind of like uh stacked things. Like can you just like tell me like what's variance of x is in terms of expectation? So here I don't assume zero mean. Let's say in general. Yes. Um. Uh-huh. Yes. You need to. Okay. This is like okay. At least some of you got it right. Right. So what's the variance defined? What's expectation by the way? When I say expectation of fx here, it's really just let's like consider discrete variables. So it'd be something like fx, this function of fx multiplied by probability mass function x, right? And sum over x, right? Something like that, right? That's the expectation, right? So it's just taking the average of fx, right? Taking different value of x, then you weight the sum the probability of occurrence of each of the x, right? And then like if I consider variance, uh, it should be uh, yeah, it should be x minus expectation of x this square. So why we have that is basically this is just the mean, right? This is the average location of your x there. And you want to look at like for each of these possible x here, let's say x, I can take several values here. Let's say this is a distribution of this x here, this is x here, right? The mean is somewhere here, right? Let's say mean is here. This is expectation x here. Now I look at like each of these guy, like how far from the mean, right? And then do a weighted sum of that. Uh, how far in terms of the square distance, right? I just square that, and then I take the average of that, then get the variance. Okay. Um, and by the way, like uh, we have something I don't know. I mean, like maybe I just give another question, just check your background or something like. So, if I have x and y variable that are independent, let's say x independent of y. So what will I have? Like I will have, let's say, uh x y equal to 0, uh x y equal to let's say wait, but like this, or maybe this is a choice, multiple choice, a b or c, maybe like e x plus y plus e x plus ey. So what's the condition of independence? Okay, that's good. Yeah, okay. Yes. Actually, this is not if and only if that's yeah, I more precise it should be then, because a C is always whole. C is always true. This is always true. It doesn't depend on like if your variable is like it doesn't depend if like they are independent or not. So, but if they are independent, then like you will have that. Actually, more precise is say if it's independent, then it's like uh, so-called uncorrelated, the variables. And if the variables are uncorrelated, then like it will be B, like if and only if B basically. Um, and uncorrelated doesn't necessarily to be independent, but like yeah, it's a little bit weaker condition. Because I actually what was independent? Remember, like okay, this you must know, right? Independent is something like that, right? That I think like you learn it from your first probability class, right? So when we have like x and y are independent, then like px is equal to py. I'm actually like this is a very reasonable because you think of like what is pxy using base rule. You remember base rule is like that, right? Px given y is equal to p xy over py, right? So therefore, it means that pxy is equal to, by base rule, py, like p x given y, right? This is by base rule. So then, like, if I have this equal to this, that means that what? Like px given y will be just equal to px, right? Because my py got cancelled, right? So px equal to px given y. What does that mean? It means that, like, I don't care what y you give me, the distribution of x is the same as I don't know about y, right? So therefore, like, definitely x and y should be independent. And if I have like x and y independent, like this here, like this here, then I have what? Expectation xy is what? Expectation xy is just a sum over x, sum over y, pxy, x and y, right? And but px, py, this is px, py, so it's like px, py, sum over y, sum over x, x and y. And now x are all independent, like, I mean, like, in terms of this sum over y, like, these are just constant, right? So I pull it out and I have px, x, sum over x, and then y, py, sum over y. So therefore, this will just give me expectation of x, expectation of y, right? So therefore, you see that, like, if I have independent, then it will be uncorrelated. Like, basically, I have this thing here. But the reverse doesn't necessary to be true. Um, so so let's say I assume this, like, if I get back to my weight initialization problem, let's say I have this y is equal to this sum here, right? And I want to make sure the variance are the same. And my variance, now I just make things zero mean, is make it simple. Um, I have like variance of, oh, okay, by the way, this is another thing, like, let's see. Okay, maybe I give you another multiple choice, just see, like, if, like, you guys check with your probability and stat background here. So I have like variance a plus x plus ay. It will be equal to variance of x, variance of ay, or maybe like write like this, axy. Maybe I make it like choice A here. Choice B, maybe a variance x, let's see, variance x plus a variance y. And choice C, let's say, variance of x plus a squared variance y. So which one is true? I mean, like, this should be equal to which one? Okay, that's good. That's good. Yeah, that's very good. Because there's a tendency that, like, I guess, if I don't give you this choice, then maybe, yeah. Actually, from my experience, and many students will thought this thing, like, have a tendency, like, thinking like variance of ax is equal to a variance of x. But yeah, be very careful. It will be a square of that, because you can think of like what's variance of ax is like expectation. Let's just use zero mean. Assume zero mean, that's easier. This thing, that will be like a square, right? So I have a square pull out expectation x square. So and and then you see, like, immediately it should be like have a square here instead of like just a. So okay. So let's look at the variance of this guy here. So variance of this guy um will be basically equal to, therefore, like uh oh wait. I guess I could have missed something here. Let's see. Okay, let me expand this, and then I worry about that. So this guy definitely will be equal to sum of this variance of this way. So that is always true here. Variance wi xi here, I equal to 1 to n. Now I'm going to argue that like this one is actually, I can write it as, I mean, or like maybe I just write one here. Variance wx here, just a particular wx here, will be just equal to expectation of w square variance of x plus expectation x square variance of w plus variance of x and w. Okay, and variance of w. So let's show that this is not something something very obvious, I guess. Like let's quickly show that. So I have, let me clean a little bit. Yeah, okay. So let's start with just consider variance w and x here. So variance w x here will be like expectation. Here, let's not even assume still mean here. Expectation w x square. Okay, you guys also know this equation, right? Expectation x, variance of x is equal to expectation x square minus expectation x square. Yeah. So this is, I just, we get this from like if I have x expectation x this square. If you expand that out, you will get this. You have, yeah, you can do it as exercise, but you expand that out, you will get this. So let's use this one here. So then therefore like variance of wx is equal to this minus this, right? And so here, like now I'm assuming like stuff are uncorrelated. So x and w I will assume to be uncorrelated. Yeah, oh, okay. I'm sorry. Actually, I say like x are uncorrelated. No, I'm not assuming that. Actually, I just assume w and x are uncorrelated. It makes sense, right? Because you don't expect that like I mean, if you input like different things, you just like modify the weights, right? The weights should be like somehow like independent of your input somehow. So it's a good assumption actually. So I will have like this will be equal to, I mean, okay, maybe I just first write, oops, first write this as a w square x square here. Now w and x are independent, then w square and x square will be independent as well, right? So therefore, like w x uncorrelated by the same manner, w square and x square will be uncorrelated as well. So I can write like w square expectation x square here, right? And this one, yeah, this one the same thing. Like I assume it's uncorrelated, so therefore I expectation w square expectation x square here. Right? So yeah, that's variance of WMX. And then now like variance of, and for this term here, let's look at this term here. This term like variance of like W, or like let's start with X first, times variance of W is equal to expectation X square minus expectation X square times expectation W square minus expectation square W, right? Okay, so if I expand that out, then I should have, okay, expectation X square, expectation W square. So I have this term is the same, that's good. Then yeah, I have also like this one here, right? So I have like yes, I have like expectation square X. Okay, this will be plus sign. Let's make sure my sign are correct. This is a little bit ugly, hard to read. X square W squares. Okay, yeah. So let's see. So then let's see. Yeah, actually, yeah. I guess you guys can substitute that, right? So I have this one here. Is this guy, and this one is this guy. Actually, I guess I will just stop here, and then like if you plug that in on both sides, you will see that this actually this whole this equality this equation whole. So let's take it here. Let's instead of going further. So I have this. I have this equation here. So and then now I apply this equation to this guy here. Then I will have like the variance of like sum over wi xi will be equal to sum of I equal to n. The variance of this is a expectation w square variance of x plus expectation, or I have this index I here. Let's put that index back. X square I variance of wi plus variance of xi variance of wi. Okay, so let's see. I would say some of this term I can just assume to be zero, right? So I first thing like okay, let's assume things are zero mean. Like assume your input is zero mean. So if your input is zero mean, then this one will be zero, right? So this will be zero. And if I also like assume the weight zero mean, so I have this one is also zero. So the only thing left behind is just this one. So I have just leave behind I equal to 1 to n, range of xi, range of like wi here. And if I have like for all the weights, let's say if I use the same, basically you assign the same variance, then I will have, I can replace this by variance w. And similarly, if my input like with no particular reason, if like they have the same variance, I will have like variance of x here. Then I have sum over n, so I have n of them here. So this one, I hope to be like, remember what we hope. We hope this guy, the output have like same variance as the input, right? So it's I hope to be like close to variance of x. So that give us the the variance of W should be approximately 1 over n. Um, and uh, and basically like this, I guess the first work yeah, I'm not sure I'm really correct by the history, but I believe the first work like is by Xavier and he is around 2010, and then afterward there's many works along this line, and know that like this one here, I assume that activation function is identity, right? That probably is not very useful here. Now, if I change to a more realistic situation, let's say if I change it to a value here for the activation function, so then in that case I probably like need to be very careful, but but we cannot use the same initialization like this. Like this one probably will not work. Like mm, basically, okay, let me write it here. The initialization that we just came up with, like I should initialize W as with the variance is like 1 over n, where n is like the number of input. Maybe I write like n input here. So this W also like 1 over n input. Of course, like the input here says in each layer can be different, right? So n input here will be the number of x here basically correspond to I mean the dimension of x here. Um Now if I have that's the case, like this is a good initialization. If my activation function is just a dummy, that is basically useless. So let's say if my activation function is a value, then in that case, how should I modify that? Uh, you see, like actually, I didn't need to worry too much about that. Um, the situation would be like this: like if let's say if I have uh what we show earlier is what like we have the if I have W here, let's say let me just focus on yeah, let me write like this is okay. I've W1 here, I have X1 coming in, Y1 here. So what we show earlier is that like the variance of Y1 uh will be kind of equal to the variance of X1 times variance of W1 times N, right? So basically the the number of X1 here. Now then but we have this activation function that like y will not go, I mean will not go directly to the next layer, right? But it will go through the activation function. So what's the variance of x, by the way? What do you expect the variance of x here? So if I know the variance, okay, maybe I should say the variance of y. In terms of variance of y, what do you expect? X to be variance of, maybe I'll give you some multiple choice again. A is like 2 times variance of y, B is like just variance of y, C is a variance of y over 2, let's say. Here, I assume that like basically I have y will go for a value here and then go to x here. So then like after the value function, what do you expect the variance of x become? Okay, I okay, my cat is not happy. Uh um actually in this case I majority is wrong. Uh okay, first of all, like B probably not a very reasonable think of that like what's value is doing. Like you have value here, and you have X Y. Okay, know that like Y is a zero mean, basically like X is zero mean, Y is zero mean. Like so therefore like Y should have like positive and negative values. So what the value does is like basically for all the negative value, it will just set to zero, right? And if I have positive Y, it will just set to okay, set to it. I mean let it pass through as itself. So think of energy. Think of like energy of like X. The energy of X definitely should not be equal to the energy of Y, right? So energy. uh, and often, like if you consider zero mean the energy, like it's essentially the same as like the variance, and actually, uh, your oh, actually, you guys are right. I'm sorry about that. Like I see like wait. No. Yeah, it's yeah, it's still like should be halfway. So you see like x2 here, like compare with this guy here, y1. After it passed through the valute, essentially cut off half of the energy, right? So therefore, it should just like get one half of that. Uh, you guys agree with that? So therefore, like x2 here, the variance of x2 is actually one half of like variance of y1 here. So therefore, like if you think of like now, it's like from one layer to another layer, from x1 to x2. If I have an activation function in the middle as well. So what I want eventually is I want the um, variance of x2 is not going to change. So approximately equal to the variance of x1, right? And I know that like variance of x2 is actually equal to variance of y1 over 2, right? And I know right, variance of y2 is approximately variance of x1, variance of w1 times n. So should over 2. So therefore, what I want will be like this should be equal to 1, right? So in other words, I want to have the uh, variance of w um, uh, I cannot read. Okay, yeah, variance of w is approximately 2 over n. So you can so then you can initialize this maybe like with as a Gaussian, let's say like as a normal normal random variable, and then adjust like the range to be like 2 over n. And yeah, this is like yeah um kind of appropriate rate initialization. And uh let's see, maybe I just show here like uh this is like if you do the appropriate rate in initialization, then like you go for like many layers and you still have the energy like not diminished to zero, or like it won't kind of like overflow to infinity and so on. So and there's many like rate initialization method. And uh I what I talk about here is a is basically the one by her in like 2015. And but as I mentioned, like Banjo like and Sapphire like started that like in 2010, I guess it is. Um, in practice, I if your if your lateral is not too deep, you probably can get away like without kind of like doing careful adjustment of your weights, like careful weight initialization. But if your lateral is deep, then like this is actually essential. Um, and I'm also like in terms of the uh, let's see if I can find a uh, yeah, it's okay. I guess I'll in terms of like I don't know whether you guys use a I'm not familiar with like Keras and TensorFlow, but in PyTorch like um if you use different activation function, then like you can have like different adjustment of this so-called gain here, because I for example, like if you have an identity function, you can consider the gain is one, and then if you have like value here, you can have like gain is one half or something like that. Actually, it should be two here, like two times, as the case of like um, um, as like when your activation function is identity, and in let me just copy this line here. Yeah, in PyTorch, for example, like you can you can do something like that. So you can, for example, if you want to use Sapphire as initialization, it has a uniform version and also have a Gaussian version. So if your uniform version is a uniform, then this with the weight here, the weight you want to initialize, then the gain will depends on your activation function. And in PyTorch, it allow you to compute the gain as well. Like, I mean, you don't need to basically compute yourself. Like you just, okay, like use this calculate gain and then like specify like what is the activation function and give you back the appropriate gain. And then of course you can change this with like different initialization method. For example, if I don't want to use Sapphire's one, I can use a coming host one. So he has the one is a coming, I guess a coming uniform, something like, or coming normal. Yeah. And yeah, okay, this is about weight initialization. Like by the way, like you see, like he has this underscore function here. So this is like, okay, where's my pen? Okay, that's my problem. Like I can just like have things disappear in front of me for some reason. Uh, oops, this is really crazy. What did I do? Did I drop it? Oh, here. Okay, I'm blind. So one, so know that like you have like this underscore like here. Oh, okay. By the way, like anyone know what's this underscore for? This is like some Python convention, I guess torch and Keras convention or something like that. Maybe not Keras, NumPy as well. I guess use something like this. Um, um, yeah, I. So this is like doing in place operation. So something like if you have this underscore thing, like you have an input W, it just directly modify the W here. So if I don't have this underscore here, it will just return a weight here. So then you will just probably like to use it then appropriately without the underscore will be something like this is equal to the weight, like W is equal to this guy here. Uh, but the underscore version is preferred because you don't need to like kind of assign a new kind of another memory bank um, to just like, I mean, assign more memory to duplicate this W here. So okay, that's okay. That's all I want to say about weight initialization. And then, of course, you can just dir this thing like and then init, for example, like to see like what kind of like initialization you have, and then you can read the documentation to say what you want to use. Yeah. So okay, and Any question for that? Let's see what I, oh yes, I want to keep this notes here to see what I want to talk about. Um, so we cover weight initialization. Okay, next thing I like to mention is like batch norm. I guess that maybe some of you already know that. So probably even using that like when you're having a network. So the idea here is say for example I have a new network here like still multiple layer. Um, I I may want to control my for example let's say in particular if I'm using not ReLU here, maybe I'm using sigma here or a tangent here. Oftentimes I don't want to fall into the saturated region because I then, as we mentioned like several times, that like backport won't be able to backport. I mean, come back a non-zero like gradient basically. So to one way to ensure that is like maybe I can control the range of my input just before the activation function, right? So if I make sure that like, let me just zoom in here. So I have an activation function here. Let's say maybe tangent or sigmoid. Okay, I cannot draw nicely. So here, maybe I'm more interested in region here so that I will have a non-zero curve gradient. Uh, if I'm around here again, it would be bad, right? So to ensure that like, what I can do is like just before getting into this activation function, I may normalize that. So for example, like if I have the values tends to be biased, say to be like pretty big, then maybe first thing like if I have input like going into this activation function, I may want to like set it to zero mean. So maybe I will subtract the mean there, subtract the mean, maybe x minus the uh, what they are used here. Let me call. Let me repeat. Okay, let me call it this x again. So forget about this what we call earlier. So let me call this x again here. Just say that this input to the activation function is x. Um, and what I want maybe I want to subtract x by its mean, right? So by its mean there, and then maybe I want to normalize uh, the scale this to within this range also. So when I subtract the mean, I will be like move around to this position here, right? But if my x has a large range, then maybe like it still will be over 4, right? Then maybe I can like divide by its variance basically. Actually, more precise is with the divide by the standard deviation. So the square root of the variance, something like that, right? So before I getting into this activation function, now I have my x here. Like now I inserted another layer here. So before to this activation function, I call this x hat here, let's say. Now I will have x hat equal to this, something like just move my any data that potentially say far away the operation region, I would say like the operation region, operating region of that activation function back to the operating region. So does it make sense? and and uh, and then like the problem is like what should be the mean and variance like because like, if I only have one sample coming in like I need to do some statistics to determine this mean and variance, right? So and that's where the batch norm means. So I when I say batch norm, I will for the entire batch, right? We do batch training, right? For the entire batch here, we'll compute the mean based on this batch, basically, and compute the variance and the mean based on this map batch here to have an estimate the variance and mean here. So that's it. Pretty simple. And now the question here is also like, so but is that always a good thing to do this normalization is hard to say, right? So maybe it's good, maybe it's bad. But one thing we can do is like uh, we can actually maybe I can just show this slide here, maybe even. Okay. So this is just what I said here. So we can normalize that input here into this one here. And the batch one therefore like, is typically added like insert just before the activation function. So for example, like above just before the 10H function here. And um, so we it's not guaranteed that like doing this batch norm is better, right? So I mean, it's always like the case that you is have the best interest to shift everything to the norm there, right? Maybe in some sense, maybe in some situation, maybe for that feature is actually bad. uh, in that I want to ignore the feature, or like I want that, or like that is actually a dummy that I shouldn't consider that should be always activated. So then the artificial move um to zoom in, that may not be a good idea. So what can be done is like we may undo the situation here, like so right after normalizing that we can just add back some potentially okay, I add back some kind of bias and then scale it up by some other parameters. And the point is like these two parameters here can be trainable, right? So here we can add just two parameters here that allow the model to train, like during training. So we do the batch norm here, but like we also insert like two parameters for it to train. And if it turns out that it's good to normalize as we want, then like as here, okay, okay. If like if batch norm is doing a good job, what should be like gamma? Or like if this is great, then what should be gamma and beta here? Maybe I let me let me let me also open this with Suno. I guess easier. So we're here right, somewhere. I don't know. Let me go all the way down. So as I just mentioned, so if this is a good way to do, so in the sense that if if we are really like doing, I mean, uh, what I want to say is like if if for the case that like shifting x into the zero mean and also like normalized to unit variance, if it's doing a good job, then what should be the gamma here? I'm not sure my question is clear. What's the gamma and beta here? Yes. I guess my question is not so um so and if in the case that like it's good to shift to zero mean and unit variance, then you train the variable there, then the variable should end up just one MCOA. This one not going to change anything. On the other hand, like if this is not doing a good things, then you can also or like not you but like training the model itself will automatically undo that, right? So you can undo this operation if turns out that like okay if we have gamma to be like the variance of like x here or like is equal to standard deviation here, or I should say like square root of variance of x here, then this will just like exactly reverse this like division, right? Division operation. I'm also like if I have like beta is equal to expectation, right? Equal to the mean here, also like reverse this operation, right? So I will get back the original x here. So I mean like having these two parameters also allow you to undo this operation. Like in case this operation is not good, then like this is able to undo that. Yeah. So and this is batch long and okay, I guess I maybe I just move this. Oops. Okay. Yeah. I guess I maybe I just keep using this and then yeah. So okay, let's explain like to mention like probably also like if you guys already uh have like playing with neural network before, you should be familiar as well. Like um I cannot so like to mention dropout. So you can think of dropout as a form of regularization. So the um okay, yeah, here I have that. Yes, maybe I use this one here. So let's say I have like just a network here, like multi-layer networks. So the idea of dropout is like during training, I just randomly set some of the new ones. I just assume they're just pretend they're not there. So for example, like here I just say pretend they're not there, I remove that. So then like the only connection I left, like I will just let the remaining connection to connect it and then create a network. I'm training this network instead. And every time I just like have a different location get uh erased basically, and then change again. So um and this turned out to be a good thing. Um at least in some situation. Actually it's also like this is like some of these um I mean neurological research is like going so quick that going so rapid that I it's interesting to look at some literature research to see like whether dropout is still um I think it's still relevant, but like also you see that like also there are works that like they they don't use dropout. Um, but yeah, but I guess like, it's good. Like actually, like, it's always something is good to try. Like if you it's actually very again like if you're using packages. So like even if you implement from scratch, this is a very simple idea. So just each time that you erase some of these nodes and then like and then I connect them. So okay, okay, I'm train them. So okay, but one thing like maybe like consider why this work. Like so why this actually do potentially even like why this actually can give us better result because like of course like this is like by Hinton like so Hinton described that and then proposed that uh at the beginning, like people think is actually a crazy idea. So and then afterward, like people try to describe, explain like why it works, at least in some situations. Um, one I guess I probably the best argument for this one is that uh, think of like ensemble of model. Um, for example, like you if you also do like other machine learning, for example, you do like decision tree, and like random forest, and you can interpret like random forest as a ensemble of trees. And like when you have ensemble models, that basically what I mean is like you you have like trained several models, multiple models. For example, like I have again like a very simple problem, like to do like classification of cat versus no not cat. Then if I have like different models here, like multiple models, and I can apply, I mean, I can utilize these multiple models to make decision by simply doing like majority vote, right? For example, if I have 5 models here, and if I have like 3 out of 5 saying that this is cat, then I would say it's a cat. Otherwise, I say it's not a cat. Typically, if you use ensemble of models, you always get a little bit gain compared with like independent models here. So the way to interpret, okay, one way to interpret why dropout will give you like better performance is that like you can think of this is actually doing like also ensemble of models, because each time you train with a different dropout with different nodes to be dropped, it's essentially you're training a different model. And then like when you appropriately combine this model together, then you actually have like an ensemble model that each that supposedly will be like better than should have better performance than each of these individual model like here. So another rationale people argue why dropout could be a good thing is that like if you just try to train the entire model here, potentially you may stop like whenever you have kind of like some part of the lateral is doing really good things already. For example, like maybe I'm trying to again to doing a kind of cat no cat recognition here, cat versus not a cat, and then maybe I managed to have a part of the lateral doing like really good, just maybe like this lateral doing really good. And based on the training data, I'm saying, okay, I'm classified as a cat whenever I see something like with a tail, something like that. And this part of the lateral essentially just detecting whether your image has a tail. And maybe like all your data also like for the cats is also like cats has a tail or something like that. Now, if you do dropout, potentially what happens is like sometimes you will get like this part of the lateral got erased. You're forced to use other part of lateral to train to learn other features of the other of the image. Maybe like since you are not relying on this tail anymore, maybe here you try to like train other parts of the lateral to train to identify ears of the cat, and so um that will give some diversity of the model that presumably will make the model more robust and generalize better. So okay, that's a high level dropout idea. So finally, I just want to mention one caveat here. So when using dropout, of course, during training, you are basically randomly dropping nodes, right? For example, like let me consider a very simple. Maybe I shouldn't show you here because I want to ask question for you guys. Uh, let me maybe move to here. Oops, oops, oops. Ah, why? Okay, now it's okay. So let's consider a very simple case here. So let's say I only have two nodes. Let's say I have two nodes here, like X and Y, and then like or like two input here, X and Y, and then corresponding way W1, W2, and then add together I have like A here, right? And when dropout happens, so what will happen is like maybe sometimes I will drop out this node, sometimes drop out this node here, right? So and let's say if I just have to assume the drop probability is like maybe one half, a probability that one half probability dropping this one half probability dropping this one, and so on. And I actually I have I also have like uh actually I have 1/4 probability that I have both of them drop as well, right? One half each. So now during test time, let's say during test time, I have this during training, I have this train this W1 and W2. And let's say I train it like within dropout. Sometimes I drop this, sometimes I drop that, and then I got some node train. Um, so let's say like I have four situations here, as I just mentioned. I can have like either uh, X and Y both are not dropped. So if they are not dropped, then I have a quarter of probability to be not dropped. And then maybe my train parameter is like W1X. Uh, train W parameter is W1 W2. So I have the input here, the output here. Let's say the output here, if I want to see what's the expected output here, right, what's the expected output A will be, in this case, will be like W1 times X times W2 times Y here. Uh, if this both of them are not job, right? But this is only occur like with a quarter probability. Or I can have situation that like maybe this one is drop, this one is not drop, right? So in this case, I essentially it's like W1 is not there, right? Because it's dropped, then this is not there. I only have like W2 times Y, right? You agree with me? So it's like if this guy is dropped here, then like that's nothing going to pass here, right? So my A in that case would be just equal to W times Y, right? And I also have situation that like maybe this side is dropped, but this side is not dropped. Then I will have like W1X instead, right? Or I may have both of them drop, right? Then I will just got 0. Now then my expectation A now will be equal to what? It will be equal to this all add together is equal to 1/2 W1X plus W2Y here. So let's see. I'm thinking to frame a question here. Uh, Note that like this is training time, right? This is training time, right? This is training time. Then what may happen? This is training time, and and I'm doing testing. Of course, okay. This note that like I here I assume a little bit like I'm not quite rigorous here because like this W1 W2 like different training. For example, like this is like the situation when they both drop, maybe like in that. Oh, sorry, both are not dropped, then I train to get like W1 W2 two different values different from this guy here. But here I'm showing more or less the mean of that. Let's say like this is a if like in the second case here, if like the if this one is dropped, then I only training this one here. I have a W2. This may not be the same W2 here, but if I just consider the mean, then let's say like I just put the mean together, then on average, during training, I'm expecting the output here is actually equal to this guy here. Or actually maybe so maybe I put more rigorously, maybe like expectation W1, expectation W2 or something like that. Now then doing testing as well. Doing testing, like so you see something that's not kind of like if I just use W directly here, something will not add up. If doing testing, I'm also expecting like my output. Why is shaking here? I don't know why. Is there something like okay, like because of my mouse actually? So if I doing testing, like let's say I have this W1 and W2, my question is like, what's by my rate? So let's say after the training, let's say I train it now, have when I train the model, like each time you have you get a different W, right? So or like I should say, like each time you drop out like either this side or this side or like both of them, and I have some W, right? And then you consider like let's say after training you have the eventual W now, you have the final W now. Now during testing, so I also have like some X and Y here. So my question maybe I also like put like some maybe ABC here, some multiple choice here. Which one is a correct uh, testing weight here? So should I have uh, W1 maybe my like I might give an index here, W1 test, maybe superscript test like should be equal to W1, W2 test equal to W2, or W1 test is equal to 2W1, and W2 test equal to 2W2, and W1 test is equal to 1/2 W1, and W test is 1/2 W2. So which one should be correct? I guess this is the last question, and then I will end here. Is that maybe I'm not explaining very clearly here, but so you see like what's going on, right? I have during training, the training procedure is I randomly drop out things and then train the W. Um, and continue to train. Eventually, I get some W's here. And testing, yes. So I mean, like, okay, you have to be careful. Like, during training, like I actually what you see is during training, I I have like if you think of like again like in terms of energy, like because sometimes like you get some of the nodes get disconnected, right? So during training, yeah, I also like thinking like, okay, this one is definitely not correct, but usually I will have confusion. I write this one or this one. So I should be have the W. Yeah, I think the W should be get reduced. Let me make sure during testing. Yes, 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 yes. Yes, yes. C is correct. Yes. So during testing, like, so you see, like, I need to make sure this is a training and testing is basically the same thing here. So because of the dropout, the expected output here, like, you only get half of the energy, like during training. So, and during testing, you don't have this dropout, right? So you always use all the nodes, right? So you want to make sure that it has the same amount of energy as the same situation of training. So therefore, you should have the weight reduced by one half. And yeah, I guess I should maybe just a final remark quickly. Then, so, and of course, you can do something like, you see, like what we did here is like during training we train the W, and then like testing we scale it down by one half, and you can also absorb this. Like basically, like you can absorb this like up one half, like, or like P in this case, like one half is actually a drop of probability P in during training as well. Then like during testing, you don't need to scale by P. But yeah, but it's actually very minor. So okay, I guess I will just stop here. So like I'll see you guys next week. So uh, and okay, yeah, thank you. So I'll end the meeting now unless you guys have any questions. Probably, okay. So okay, I'll see you guys.